Okay, let's complete this identification with an example. This example comes from a future chapter 8.2.2, but I want to do this example also with method 8.1. So what do we have there? There is a given process with 3 PT1s with 3 different time constants, and the K is 3.415. Remembers to pi, so that's true. 1.5 seconds, 0.7 and 0.6 seconds. Here we have the 1. So again, T1, T2, T3 are given. K pi 0.7 seconds, 0.6 seconds. We need the step response. We do this with Csii. Then I print this out, draw an inflection tangent, define the TU, TG, and then calculate the TA and TB with my Reuter module in WinDF-C#. Okay, let's start with WinDF-C#. In my signal block editor, if I start it, the program language is German, so I switch to English. Then I need my 3 blocks with the gain 3.1415. The first time constant is 1.5 seconds. Then the next PT1 is gain 1 and time constant 0.7, and finally we have a time constant 0.6 seconds, gain 1. So okay, we connect the blocks with branches and can produce now the step response with this button. We want to see the output block number 3. Input is only one input with the number 71. If I calculate the step response, you see this is the beginning, not the end. We need the final value for my TU-TG calculation, so I increase the time range, recalculate this curve, and here you can see with a fine grid that the final value is reached, so that I can draw a line for the final value to find the cross point of the inflection tangent. Okay, I print this curve on my printer. That of course I cannot document. I do this in parallel now. I stop this recording, print it, draw the tangent, and show you the result. Yeah, wait for the result. So look what I have done. You see here the curve. This is my step response. I draw the final value, a straight line. I draw the inflection tangent. Then I get this cross point, the time between 0 and this cross point. I measured was 1.4 centimeters. And the time between this point and that point I measured with 7.2 centimeters. I multiply with the scaling of this diagram and get 2 time values. TU is 0.667 and TG is 3.43 seconds. So this is the result of the manual identification with the inflection tangent. These values I have typed in the WinDF-C# module, so I make a note. Note with I have got TU is 0.6667 seconds, and Tg is 3.4 seconds. Okay, now with Reuter I have typed in the value 0.666 and 3.43. Don't be confused with the more digits here. I typed this in, and you see the Tu over Tg ratio is larger than 0.104. It's nearly doubled, so automatically this program adds a delay. This field was colored so that you don't forget to add a delay in your curve, and he calculates two time constants, T1 and T2. So the model result I note in my paper is TA, is that what the program throws out, 1.5946. TB is 0.9566, and there is a delay TD which is 0.323. So this is now the resulting 2PT1 delay model, and the question is, how can I compare? I do two comparisons. First, if you compare the numbers, you see I have two time constants here and 3 there, and these numbers have nothing to do with these numbers. The sum, 1.6 and 2.6, the sum is nearly the same as the sum here, but the single numbers, of course, are different. So the numbers cannot be compared, or if you compare, say, they're totally different. Yeah. So the question is there a better comparison? I do two comparisons. First, with step responses, and second, with reference step responses. Yeah, with reference step responses, as I have indicated in the beginning of this chapter. Yeah, I go back to the beginning of this chapter. You see, no, not right. That is on another screen. So I go back to another window. Yeah, slow computer. Where is my text? There is my text. Yeah. I have done this. The first check, I compare numbers, but the number comparison is worse. Then I compare the step response of model A and the step response of model B, and then we'll see, good coincidence, but the best comparison is my 3PT1 model here and my 2PT1 and delay model here. I used to calculate a controller. I design a controller with model B, put this controller together with model A, and check the reference step response. Before I do this, I design a controller with model A, because if I know model A and design a controller together with a known model, this gives the best result. So I can see the best result if I know all time constants and then the identified control loop with identification. Okay, not to be confused, let's start to do the job. First, I go back to my page. Okay, first I have a step response of this. I have drawn this, so I think I store this curve and fix it. Then I store this 3PT1 plan to recall it later for a controller. I store this as a 3PT1 block. Store. Yes. Then I change this block into my model, identified model. So I have to delete this block and replace with delay time block. I overwrite now the results. The delay time was 323. The block 2 gets now a new time constant, which is 0.9566. 9566. And finally, with a with the right mouse button, I can now, I think the K cannot be defined better than 3 significant digits, 3.15, and the measured time constant is 1.5946. So this is the identified model. I store this, I save this to say this is 2PT1 delay identified 8.1. Identified 8.1. So this model also produce now step response. Wait for this. Don't forget to click this button before I have done this. You see the next curve is written in a red color. If I recalc this, you see a very good coincidence. A red curve is my identified model with it turned with inflection tangent. So you see a rather good result. But no, I think I should go into the next comparison. I want to compare reference step responses. First, again, I design a controller with my original model. So I delete this so that you can see really this is gone. I load now my 3PT1 model. These are the values, original values. If I click on this button, you see 1.5, 0.7, 0.6, original model. Then I add a controller. Default values, we want to design it automatically. Then I add a summing point. And I add branches. Close the loop. Now I use the design method of here this tool. Then we need a minus sign to have a negative feedback. Don't forget the minus sign, otherwise this doesn't work. Then we start the controller design. We want to have a design step depth of 5 is a rather good design. Then the program proposed TV constant, we want to have this. We have no other idea. We can of course make pole compensation with a known time constant. So why not? We can override this with my second largest time constant, which is also possible. I know them, so I could use them. Say OK, and I make pole compensation also with my PI. You see the proposal is 1.59. The known time constant is 1.5. This program uses the minus 12 dB method. We want to have 60-degree phase margin and say OK, calculate please the PD. You see now the Bode plot, ignore it. These are the parameters I want to note now on my screen. So shift them away, open my board and say OK, controller with 3PT1 model gives Tn is 1.5 seconds, TV 0.7 seconds, manually typed in. Note, these are the values here. Largest and second largest one. Step depth is 5, given by my task. Phase margin should be 60 degree, given by task. And the result of this is a Csii value, which is 0.3911. I calculate now the reference step response in my system. And now I delete these step responses of the process, because now I have step responses of a control loop that are totally different. I open the signal block diagram editor to see the numbers. If I want now to see the reference step response, I put a unit step function at block input 71 and look at the output of block number 3. So just click on it, recalc. Here you see the reference step response of the 3PT1 model with the controller which is designed with the 3PT1 model. So best case, but not always available. Yeah. Okay, I store this curve because now it comes a comparison. The comparison goes in the following way. I close this. I store this as loop with 3PT1, and I open the identified model. The identified model now is auto completed with a controller. Say OK with the summing point. So all steps to close the loop, I repeat. Closing with mouse clicks. You hear my mouse clicks. This goes very fast. I make a controller design now with the identified model. Say OK. Yes, I want to have 5. I don't know the time constants. I just use the built-in minus 30 dB method. I accept the proposal from the program with this button. Say OK, and I accept the proposal with this button with the minus 12 dB method, 60 degree phase margin, and this is a curve with the value. You see, Csii value is different, Tn value is different. I note the 3 values for my documentation, and then we will finalize this with the reference step response. Wait for this. I just note the numbers. Controller with 2PT1 delay model has a Tn value which is 1.63 seconds, a TV value which is 0.69 seconds, step depth unchanged 5, Csii is now 0.4739. Okay, note, if I now click on this and make the reference step response, this is not a good comparison, because of course if your model now is wrong, bad, and you design a controller with your bad process and run with a bad model, this could give a good result. The best test is we take this controller we put this controller now together with the original process. That is important. So what I can do is I open the controller. These are the values I have noted, but in the PID controller there is a good button to store these values. You see here there is a store button for in the PID converter, a store button where I can store the 4 controller values in the registry. So I say OK. I store this as a loop with 2pt1 delay. Loop with 2pt1 delay, and I open the loop with the 3pt1s. So you see, this is now the original PT1. That is at this time not that controller I want to have. That's the controller with the 3 PT1s. But now I go into the PID-T1 converter box and make a recall. You see here, now this recall gives the values I have derived with my identified model. Say OK and go into the calculation, and you see the reference step response has a little bit larger overshoot. Here it is a little bit faster. Final value is okay. PID-T1 has always a good final value. But you see here that is a true difference. Quality check. Is my identification acceptable? And you can see, of course, acceptable, not worse. A little bit faster, a little bit higher overshoot, depending on the specifications. You can live with this. If you say, okay, the overshoot is a little bit too high, then of course you can decrease the gain a little bit. Then you have a better overshoot. But I think you see here, this identification method is rather acceptable, rather good. Okay, so I can stop here and start with the next chapter.